Okay, so in this video, what I want to do is just have a look at another example of a first order differential equation using Laplace methods to solve it. So we've got dx by dt plus 2x equals 10e to the 3t. And the initial condition is when t equals 0, x equals 6. So first things first, let's just rewrite this just in terms of notation that we're familiar with. So we've got x dot plus 2x equals 10 e to the 3t. Yeah. And we know that the Laplace transform of x is, we're using the x bar to represent that. And if that's true, then we can say the Laplace transform of x dot, the first derivative, is going to be s x bar minus x naught. Then the Laplace transform of the second derivative, which we don't actually need here, I have a bad habit of doing that, is s squared x bar minus s x naught minus x1. It's good to do the second derivative actually always because it just gets rid of the habit of higher order derivatives for transforms. It's useful. Fine. So now we've got this x dot plus 2x equals 10e to the 3t. If we do the Laplace transform of the left and the right hand side, incorporating the principle of linearity, we're going to get the Laplace transform of x dot plus the Laplace transform of 2x equals the Laplace transform of 10e to the 3t. Yeah? We know the Laplace transform of the first derivative of x is just going to be this. It's going to be s x bar minus x naught plus the Laplace transform of 2x, or we know the Laplace transform of x is x bar. 2 times that is just going to be 2x bar equals 10 times the Laplace transform of e to the 3t. E to the 3t, that's going to be 1 over s minus 3. So we can just say s x bar minus x naught plus 2x bar equals 10 on s minus 3. Yeah? Keep that up a bit. So we know that x naught is 6. It's the initial condition when t equals 0, x equals 6. So let's rewrite this. S x bar minus 6 plus 2x bar equals 10 on s minus 3. So we can say x bar, s plus 2, equals 10 on s minus 3 plus 6. I'm just moving the 6 to the other side, multiplying by s minus 3 on s minus 3, i.e. multiplying it by 1, which is fine. Now we can simplify this and say that x bar equals 10 plus 6s minus 18, all on s minus 3. Yeah? So we can say that x bar equals 6s minus 8 on s minus 3. Is that right? Ah, I have missed something. The s plus 2 over here. I didn't divide by s plus 2. Sorry. Okay. And that's going to be a partial fraction, isn't it? So let's see. Well, that's going to be 6s minus 8 on s minus 3. Whoops, sorry, can't see that again. S plus 2. That's going to be equal to a on s minus 3 plus b on s plus 2. So we're going to have a s plus 2 plus b s minus 3. And that's going to equal 6s minus 8. So when s equals minus 2, we've got minus 5b equals minus 20. And that implies that b equals 4. And then when s equals 3, we'll have 5a equals 18 minus 8, it's 10, and that implies that a equals 2. So we can come back up, and we can say that this is identical to 2 on s minus 3 plus 4 on s plus 2. So, formally, we can now say that x bar equals 2 on s minus 3 plus 4 on s plus 2. So if we take the inverse Laplace transform of the left-hand side, we'll have to take the inverse Laplace transform the right-hand side. And we know that the inverse Laplace transform of x bar is x. So that's going to give us our answer, isn't it? We find the inverse Laplace transform of 2 on s minus 3 plus 4 on s plus 2. So let's go ahead and do that. So we can now say that x is going to equal the inverse Laplace transform of 2 on s minus 3 plus 4 on s plus 2. Principle of linearity and coefficients, we'll do it at the same time, say that x now equals 2 times the inverse Laplace transform of 1 on s minus 3 plus 4 times the inverse Laplace transform of 1 on s plus 2. Yeah. So we can now say that that is going to, therefore x equals 2 e to the 3t plus 4 e to the minus 2t. And that's our answer.